All right, so we just finished talking a little bit about convolution and some of the basic ideas behind convolution. So in the rest of this, we're just going to talk about convolutional neural nets in particular. And simply put, convolutional neural nets are neural nets that use convolution. So what does that mean? So if it takes an image as input, right? And recall an image is some number of channels by some n1 by n2, right? Number of pixels. Then you would convolve this with some other w image, which typically is smaller, let's say h1 by h2, and then you would convolve your x with this w, and that would be seen as an operation. And that's a linear operation. If you took two of these x's and summed them together, then w convolved with the x is the sum of the w convolved with the individual components. And then you could apply, for example, a nonlinear operation, like a sigmoid, to this convolution. And this sort of this convolution, this combination of operations, convolution and then a sigmoid, and you could also, for example, add an intercept to this. This whole operation is called a convolution layer. And often we do this for multiple. Often we do this for multiple w's. Right? And so that will be considered the number of channels in the convolutional layer. Right? So you could think about this in a number of ways. You could think about this thing that's outputted is an image, right? Convolution of two images produces another image. And so then you apply the sigmoid or whatever other activation function to this, and that produces another image because it's applied element-wise to all of the output pixels. And then you would have multiple channels. You would apply this to multiple, you would use multiple different W's. Now, a lot of times you'll have an input number of channels to a layer, but it seems to output just a single image. Typically what ends up happening is that you end up contracting those input channels. And so it's actually pretty hard to figure out what some frameworks like TensorFlow and Keras are doing to all of those input channels if the number of output channels is a certain number. And typically it's just summing across all of those input channels. And so we'll come back to this idea in a minute. Other types of layers that are typically used with convolutional layers are the pooling layers, and sometimes this is called downsampling, sampling, and quite often after you do these, and we'll talk about what pooling and downsampling is in a minute, often you'll have another convolutional layer that occurs, and then of course this gets fed into, and then quite often after this you will vectorize or flatten, and then you will feed it in as if into a multi-layer perceptron. So what does all of this mean, right? This seems very abstract. So of course there's some loss, and we're building up some sort of a function with parameters w. Right? W are these images that you're convolving. Most of the time we'll call W is the convolution kernel. Right? So you're going to want to train your neural net by choosing a convolution kernel via some stochastic gradient descent type method. And so what we end up doing is we'll still use backpropagation, but we're going to backpropagate and take gradients with respect to this convolution operator through this convolution operator. And it's not hard to do this. One way to see why it wouldn't be too hard to do is, first of all, we can write the convolution in the following way: W star x sub ij is equal to the sum over k and l of wi minus k and j minus l of x k l. This is what convolution is. And cross correlation will give you something very similar, just with these indices, the signs of these indices reversed. And this is going to be equal to the sum over k and l of, we can write a large tensor, aijkl, of xkl, right? Where all aijkl is this is equal to wi minus k j minus l. It's equal to this, and then when it's where it's well defined, right? This aijkl is just equal to this, and so we can see that this is just a linear operation, a simple linear operation. It's just with very specific forms of it's just a very specific linear operator, right, on the input image. Now, another thing to note, because it can be written in this type of sum, it's very easy to take a derivative of this operation with respect to one of the W entries. So that's another thing to note. So the convolution layer can be thought of as a fully connected layer. If we look at this form here, it's like this we'll call it our fully connected representation. That's a good name for it. For the convolution layer, right? But what's the big difference between this and a fully connected layer? And why do I say fully connected layer? I just mean that each of these are different inputs, and they're going to get multiplied by a weight matrix and form the ijth entry of, and then you would get the ijth entry, which we could think of as a hidden unit, right? So this is the so-called fully connected representation of the convolution layer, but because it takes this very specific form, a lot of these elements of this tensor are constrained. So what does this mean? So if we think of this as a fully connected neural net, we have x11, x12, all the way down to xn1 and 2, right? These are the input scalars, and these get multiplied, of course, by a11, 11, and so on. This would be a12, 11, and then so on. And there are tons of these numbers that it gets multiplied by, because the output dimension is the output image. We could call it h11, h12, and so on, until we have we'll call it h1, h2, which is the size of the output image, h1 by h2. But there are constraints on these, right? There are constraints on these weights, in particular, because aijkl is equal to wi minus k, j minus l, then this is equal to wi plus 1, w, for example, I plus 1 minus k plus 1, j minus l, for example, which is equal to ai plus 1 j k plus 1 l, right? And you can create quite a few of these equivalencies that some elements of a, I, j, k, l are equal to some different elements of a, right? And so as opposed to a fully connected layer which has no constraints on a, the convolution forces parameter sharing between the elements of this fully connected neural net, right? And that's why convolutional neural nets are not as overparameterized as their fully connected counterparts. If we were just to vectorize the input image and then train the same number of parameters in a multi-layer perceptron, it would have far more parameters because it would not have these additional parameter sharing constraints. And you can see this because the number of parameters of the convolution layer is just the number of elements in W, and that's just our H1 times H2, right? Oops, sorry, that's not right. That's our the size of W, which I'll just call it P1 times P2 if W is P1 by P2, right? And typically P1 and P2 are numbers like 5, right? So it's really only 25 parameters for a single convolutional kernel. And then we typically have multiple convolutional kernels, say 25 of those. And so it'd be 5 times 25 is not that many, right? And so so that's why convolutional neural nets are better than, can often be better than just vectorizing and using multi-layer perceptrons, because they won't overfit, and they use this idea of convolution, which is well suited for natural images. And also, not only are they is there this parameter sharing, but the interactions are also sparse. So for example, if you take your aij kl, if you take I minus k or j minus l, and that goes outside of the bounds of the size of w, then you would get that aijkl is 0, right? So it's also equal to 0 if the size of I minus k or j minus k, for example, exceed the size of w, right? So this P1 or P2. Right? And so, those are the advantages of convolutional kernels over fully connected neural nets. And yeah. So another thing about convolution that makes it special is that convolution, we call it convolution, is invariant under equivariant to translation. Convolution is equivariant to translation. And what does that mean? Well, that means that if we shift our output, so x star w, if we shift our output, that's equivalent to first shifting x and then applying the convolution with w, right? And you can imagine how, if you were to convolve a small kernel with an image, and then you were to shift the image a little bit, that won't change what the output of the convolution is. And this is really for the full convolution, because you have to worry about what happens around the borders. But it really has no, shifting the image has no bearing on the output of the convolution. It just shifts the output itself. Right? Okay, so that's another thing that we would really prefer, because if you can imagine taking, say, a cat in an image and then moving the cat around, right? Moving the cat around doesn't change the fact that it's a cat. And so this equivariance to translation is something we would really like to have. Okay, so another thing that I should define, which is just nice to have for lingo, is that we have our receptive field. And this is of a unit, are the input pixels that it depends on. So by a unit, we mean the pixels of the output of convolution. So output pixels. So for example, if I had an output image and I was interested in the pixel that results from the inner product between the convolution kernel at this location, then these pixel locations here would correspond to the receptive field. So this would be the receptive field for that location. Yeah. Okay. So so another definition that I've already mentioned this, but I'd like to mention it explicitly here. Cross correlation is just the convolution with the signs of the being reversed. So it's the cross correlation instead of convolution is if you did I plus k, so xi plus k, j plus l, w k l. So this is just cross correlation. And you can get it from convolution by flipping this w. So the cross correlation kernel is the same as it's like the mirror image of the convolution kernel. And typically cross correlation is what's used in TensorFlow. Okay, so pooling is an interesting technology. So pooling, the basic idea is that we're going to apply a fixed transformation So in its basic incarnation, there are no parameters to a pooling layer, and it's to the output. So if we call this phi equal to our w convolved with x, or our sigmoid, right? Then pooling is going to apply a transformation to this thing at a rectangle Rij. So the basic idea to regularly spaced rectangles. So, for example, if you took your image, if we took our image, and this is the result of the output of a convolution layer, then if we grid it up into rectangles, then this transformation typically is going to reduce this by doing either some averaging within this rectangle. So typically this is average or a maximum, taking the maximum entry. and then it'll produce. So this will then yield a smaller image, which will have the number of different rectangles that were used to pool along as the number of pixels of the smaller image. So typically the way we think of pooling is that it sort of creates a multi-scale feature, right? Because it will, sometimes we call this downsampling. It will just, if you have a convolution layer in the output after pooling, then that convolution layer, if you think about its effect on the original image, its receptive field, is going to be very large, right? So you get these very large, after pooling, you get these very large, in effect, you have this very large receptive field for a single convolution. So, that's the idea behind pooling, and typically people will try either max or average for pooling layers. So how can we think of, and another thing that we'll see quite a bit either with convolution or with pooling are things called strides. And strides in a convolution layer is you just skip some output pixels. Right? So you can imagine with a single, if you implement a stride, in convolution, you're continually shifting your convolutional window by 1 pixel each time to do your convolution. Instead, if you use strides, instead of shifting by 1 pixel, you're going to shift by multiple pixels, and so you'll end up getting a smaller image. And this is very important to add either strides or pooling layers, because eventually you want to end up with a much smaller image size in the end, so that when you vectorize it, you're not going to have something that's highly over-parameterized. Right? So that's what strides does in a convolution layer. It also works effectively the same way in a pooling layer. It will also skip them, except that in a pooling layer, you can actually, in effect, by, oops, not sure what's going on there. In effect, it looks like I have a star now. In effect, instead of having for a pooling layer, instead of having disjoint rectangles, you could have overlapping rectangles by having your strides be smaller. I'm not sure what's going on here. Let's try this again. By having your strides being smaller than your pooling width, you can have non-overlapping rectangles. If you set your strides equal to your pooling width, then you're going to have overlapping rectangles if the strides is less than the pooling width. And if strides is equal to the pooling width, then you have non-overlapping or disjoint rectangles. Okay, so let's take an example. It's very important to think about the dimensions of your tensor when you construct a neural net. So let's start with a 32 by 32 image, okay? And then let's feed this 32 by 32 image into a convolution layer where we have 5 by 5 filters, or 5 by 5 kernels. right? And then we have 6 output channels. So typically we specify our output channels. And then so we have a 28 by 28 image in the end because we're going to only do valid convolution. We're only going to do valid convolution. And so then we're going to feed it into a pooling layer. And our pooling layer, we're going to make it have 2 by 2 width for pooling. And then this 2 by 2 width, we're also going to make sure that I think you don't have to specify this by default, but the strides are also going to be 2 by 2. And also for all the convolutions here, we're going to have our strides be 1. And so our 2 by 2 pooling is going to turn our 28 by 28 image into a 14 by 14 output. And there's going to still be 6 channels. So it's going to be 6 channels by 14 by 14 of 14 by 14 images after pooling. And let's say we do max pooling. Then we can feed this into another convolution layer, and we have a 5 by 5 kernel again, but now we are going to increase our number of channels, and this is typical, is we use another for each convolution layer we increase our number of channels. And again, we'll use only valid convolution, right? And so the output will be, let's see, we have 5 by 5 kernel. It's only the valid ones. And so it's going to produce, what should that be? That should be a 10 by 10. 10 by 10 images, so 16 channels of 10 by 10. And then we'll feed it again into a pooling. Let's say it's 2 by 2. In the end, after this, we have a 5 by 5 output with 16 channels. And so then we feed it into fully connected layers after we vectorize. So when we vectorize, we just say, well, let's flatten this image so that we forget about the pixel locations. It's only 5 by 5, so it's not going to produce something that large. Of course, it's 5 by 5 by 16 because we also flatten the channels. And now after it's fully connected, we just will use our standard loss function based off whatever the data input is and our assumptions and our desired behavior for the method. So that's sort of a typical small convolutional layer. And the basic components here are convolution, pooling, various things like increasing the number of channels is typical for convolution layers. And this will in turn decrease your image size typically by using valid convolutions, using pooling and strides. This is all these are very common things to do. And then at some point you're going to vectorize and then feed it into some fully connected layers. So this is your typical convolutional neural net architecture. And typically in TensorFlow, you just add convolutional layers, which will, you'll have to specify the size of your kernels, the number of output channels, and a couple of other things like whether it's a valid or full convolution. And then if you want to introduce strides to reduce the image size more dramatically. So that's it for the convolutional neural net architectures, because other than this, your TensorFlow or your other favorite framework like PyTorch is going to do the backpropagation for you for SGD. And then all of the optimization procedures are pretty much the same thing as what we had before. So that's it for convolutional neural nets.